basic rule, fundamental rules of counting is that you take your number of choices you have, decisions you have, and then you take and you multiply the number of choices for each decision. So, for example, here I've got 4 decisions I'm making. I'm choosing a pair of pants. I'm choosing a shirt. Isn't working. I'm choosing shoes. I'm choosing socks. So I'm making 4 decisions. So the best way to do this, honestly, is just to draw 4 lines. So 1, 2, 3, 4, and then put in the number of choices for each. So 2 pants, 2 goes there, 3 shirts, 3 goes there, 5 shoes, and 4 socks, and then you multiply them, because it kind of goes back to that whole decision tree, right? The more choices you have, this becomes 3 branches off of each of these 2 branches. So that would give us 6 branches. It's being a little laggy. So I don't know if you guys remember this one. So here, call letters of station has 4 letters. So I'm making 4 decisions. So I'm going to do 4 lines. How many choices for the first letter, for the first spot? It has to be a K or a W, so that would be a 2. Now the next one can be any letter. However, you can't repeat anything. So I have 26 letters in the alphabet, but I can't use whatever I used in the first one. So that only goes 25. And then after I use that one, I no longer have 25 letters left. I only have 24 letters left. And after I use that one, I only have 23 letters left. And then you would multiply each of these. Right, multiply each of your decisions. So hopefully that makes sense for everybody. Here is just a quick reminder about why we, oops, what the heck? About why and means multiply. And means you have to pass more than one test. I have to get a tail, and I also have to roll a 4. I have to do both things. So of my whole scheme of things, all the possible outcomes, half of them are tails, 6 of them are rolling a 4, but only one little patch, 1/12 of them, 1/6 of a half are both a tail and a 4, because you have to pass both tests. So it's a 1/6 of whatever the first thing was, and of means multiply, so we'd multiply and make them smaller, become smaller and smaller. Should have actually brought in my rubric for that. That would have been good. Okay. And then or means add and then subtract the overlap. So or means add. Or means bigger, because or means you have more ways of winning, right? If I get a tails, or if I roll a 4, either one and I'm successful. So that gives me more choices to win. So your area, your probability should become larger, and it does. You add them, and then you subtract the overlap. So hopefully that makes sense for folks. You've heard that before. Or means add and then subtract the overlap, and means multiply. And then the other thing that's kind of important is that you remember that instead of finding, if you need to find the probability of at least one, one of the biggest rules we know about probability is that all the probabilities in a sample space add up to 1 or 100%. So if I want at least 1, that's all of these things here in blue. If I want all these things in this circle in light blue, I can either add all of them up, or just do 1 minus the last guy, 0. Because we know that the yellow part plus the blue part has to equal 1, so 1 minus the orange part equals the blue part. And that just makes things a lot easier. Okay, so here's the first thing for you guys to do. You just received a shipment of 7 TVs. 2 of them are defective. You're going to select 2 TVs. You're going to draw a tree for that. right? So you're going to make two decisions. You're going to draw a tree, a TV. You're going to pick a TV. That's your first layer of trees of branches, and then you're going to draw another. You're going to pick another TV. That's your second layer of branches. So I'm going to put you guys into groups. I want you to draw a probability tree for this. So right, you're going to draw a tree with your outcomes, and then your second layer for your second tree TV you're selecting. And I want you to put. You should be putting something in here, whatever goes in there, and you should be putting things on the branches. The probabilities go on the branches. So put. That looks confusing. Put the probabilities on the branches. So go ahead and take a look, figure this one out, and I will go ahead and start your breakout rooms. Huh. Felicia and Sarah, do you guys usually work together? Who? Felicia and I think it's Sarah. Rizzo, is anybody else coming from your group, like Austin or Haley?
I know, I was just texting them right now.
Okay.
They said they were, but I don't know.
Okay. Well, for now, I'll put you in with Adam and Elaine, and I'll pull you out all the A's. So if you guys want to hop in your rooms, you can, or not. It's up to you. But I'll give you guys, say, 5 more minutes to make up this tree and find the probability that at least, and find the 2 probabilities. Maybe 4 minutes, because it's been a little while. You should be almost done with your tree by now. Forgot to turn my camera on. So 2 are defective out of 7. So I have 5 good ones, 2 bad ones. And I'm going to pick 2 TVs. So when I pick the first TV, out of 7, there's 5 that are good. So I can either pick a good TV or a defective TV. That's what could happen. So probably I pick a good TV is 5 out of 7. Probably I pick a defective one is 2 out of 7. 2 out of 7. And then if I'm not going to pick the same TV twice. I'm not going to pick it and replace it, right? I'm going to pick it and keep it. You're picking 2 TVs. So I pick a good one. Then that means I only have 6 TVs left to pick from my second TV. And of those, 4 are good. So 4 out of 6 are good. And we still have 2 out of 6 defective. However, if I picked a defective TV first, now I still have 5 good TVs out of the 6 remaining TVs. And I only have 1 left that's defective. So that should be 1 out of 6. So then the question comes up of, well, what's probably that both work? So both work means I went this pathway, good, and then good. And remember, you multiply along the pathways because this is 4/6, but not 4/6 of the whole river. It's 4/6 of 5/7 of the river. And of means multiply, so I'm going to take my 5/7 and multiply by my 4/6. And you can reduce early if you want. That's right. Well, let's do 20 out of 40 over 42. That's easier. If you found that as a decimal, you'd end up with 0.476. And then, what's probably that at least one does not work? So one doesn't work. That's this one has at least one that doesn't work. This one is bad then good. That one doesn't work. And this one, both of them don't work. So that's these three added up. But rather than adding up these three, since I already know this one, I can just do 1 minus that one. 1 minus 0.476. And that will give me 0.524. And the way to kind of think about it if you want to is at least one does not work. So that's sort of like saying 1 minus none does not work, right? Because you want at least one. At least one does not work. I would just replace that at least one with none. So 1 does not work. So if none do not work, that's the same as saying 1 minus the probability that they all work. And you're picking 2, so that's where both work, I guess you could say, since you're only picking 2. So that would be at 1 minus 0.476 that we found earlier. Such a probability. That does not work. Okay. That's how we get to our 0.524. Okay. Questions in this one? Anyone have a question about this one? Tree, 100% you're going to have to draw a tree on the exam. So you'll be given something like this where it's like good and bad, or red marbles, blue marbles, green marbles, or boys and girls, or I don't know, any variety of things that could happen. Okay. Guys are totally silent. We did that. We did that. We didn't do this one. Okay. So yes. So empirical rule. Let me just, I'm not going to worry about this one so much, but let me just ask you this. Like this A. And then for B, I'll say, or better yet, I'll just do this. The 95%. So do B first, and then do A. So B is, within, what range would you expect to find 68%, and then we'll say 95% up above it. And do you guys want to talk to neighbors? You're just going to do this quickly, or I don't know what you guys want to do. Breakout rooms, yes, no? All right, just go ahead and solve it. Take a minute. So let's see. So this is binomial, right? So exactly 2. So like Megan had said, it's something like probability of X is equal to little n, choose x times, times p to little p to the, oh dear, to the x times little q to the n minus x. So in this case, I would end up with, let's see, my n is 8, so 8 choose 2 times 0.32 to the second times, okay, so my p is 0.32, my q is 1 minus that, so the rest of it, so 68%, 32% said yes, then 68% said no, and if 2 said yes, out of 8, that means I have 6 no's. Okay, so what do you guys get for this number? Someone tell me, text me. 2833. Great. And the next one, less than 3. So, okay, fine. Okay, 5. That's good. And then less than 2, so this would be, you find the probability is 0. And you find the probability of 1. And you already found the probability of 2. So then you add it. You take that one which you found already, and you add them up. All right, so 0 would be, so the probability x is 0. That would be 8 choose 0 times 0.3232 to the 0 times 0.68 to the 8th. Right, and then you find the probability of x is 1 as well. At least one has a college degree. Oh, what did you guys get for this one? Did you guys get an answer for this one yet? Felicia? Sarah? What did you guys get for this one? 0.0457. Okay, so at least one is 1 minus the probability of that x is 0. So that's 1 minus 0.0457. So that's 0.9543. Or you could do the long way. You could find the probability of 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. Find those ones. So you already found 2 of them. So find the other 6 and add them. Find the mean, variance, and standard deviation for this. So you guys remember this is my favorite, right? Because the mean is just NP. So N is 8, P is 0.32, so 2.56. My the variance, so that's variance is sigma squared is NPQ. So 8 times 0.32 times 0.68. And for that one, you guys got, what did you guys get? 1.4, yep. 1.74, great. And then their standard deviation is the square root of that. So it's the square root of 1.74, and that was 1.32. Great. Okay, perfect. Good. Let's go ahead and take a look at another problem. This is a good one. So here, these are This is how you figure out. This is exactly how you figure out what you need to get, or what your grade is so far. So you take the weight of each one, and you multiply it by its score, and that tells you, you know, the amount that, you know, like, so like this, you scored an 80 on 20% of your grade, but you scored a 74% on 15% of your grade, and you know, it's 81% on 45% of your grade. So, you know what? I am going to let you guys think about this for a minute, and I'm going to let you pop you back into rooms so that you guys can discuss this. And I'm not going to give you guys long to do this one, 5 minutes max. So maybe hop in and talk about it. Take a picture of it, hop in and talk about it so you can figure out what it is and how to solve it. Oh, Sarah. There we go. Oh, right. Well, you want to add up the weight, not the score. Right, so 757? 757? Or is there another 5 or not? It kind of depends on whether this was, would you, oh, some people got 7695. Interesting. Okay. So we're getting a lot of people who got 0.7695. Okay, that's good. Now, so look at this person. They had like a 67 to an 81, so they should be getting 70 something. Everyone kind of agree? Their grade should be a 70 something, right? What this is really 0.7695 is score times weight. Now, if do I want the average weight or the average score? I want the average score. So it means I need to divide by the weight. That way the weights cancel out. So I'm going to divide by the total weight, which is 100, 1.0, 1.0 weight. And then the nice thing about this is then these guys cancel out and go away. I'm left with, divided by 1, I'm left with 0.77, and that's the score. and that's your average score. So 77%. If you divide it by this, then you're going to end up with something crazy. They're going to end up with like a 30%. And should they be getting a 30%? Their lowest grade was a 67. There's no way they should be getting 30%. So it's kind of something to think about. And this is another way of thinking about it, is try to figure out what you want the average of. You want the average weight or you want the average score? I want my average score. I want to know what my average score is on all my assignments. So I need to, I don't want to divide by score. I want to keep that. I want to divide by the other thing. The other way to think about it too is, remember, this doesn't change from person to person. This is what changes from person to person. So since this is what changes from person to person, you don't divide by that. You divide by the thing that's fixed, by the thing that's constant. So another way of kind of looking at that. It's a little confusing, I think, so much. Okay, this one we don't need, I don't know, we need to worry about that one. I'd rather jump to some other stuff. So let me go ahead and do a quick review of Chapter 10. I'd like to keep it pretty quick if possible. Reminder, you do have to zoom in with me on your phone before we start, being in the final. What I'll have you do is go into the waiting room, and I'll let you 8 at a time to scan your computer area, and then have you log into the computer. And then while you're on the computer, once you're logged into Canvas, I'll have you turn your phone, and I can see you in the screen right on Proctorio. Then hold up your phone and turn it off. Like, show me you turn it physically turning it off, and then set it aside, kind of away from you. Or you can set it down face down on the desk next to you so I can see it, either one. But if it's off, then I kind of feel better and just kind of put it far away from you, and then you're kind of all good. Yeah. Ideally, that's ideal. Uh-huh. No. If you can do that, then I will log you out of Zoom. Yeah. Then your phone can still stay there. But if you can't find a spot to put it, or if you're uncomfortable having the whole room kind of be viewed, then an alternative is to just once you get everything scanned, to turn it off on camera and then set it kind of far away from you, and that would work as well. Okay. Well, no, you would physically turn your entire phone off, like, so the phone is off, like the phone is not silent, but like literally turned off, like powered off. That'd be the other option. So you can either set it so it's kind of far away, but I can still see the room, and then I will log you off of Zoom. Or once you log into Zoom, or you leave, or if you can't do that, then you keep your phone with you while you scan your environment with Proctorio, and then you hold up your phone in front of Proctorio and you turn it off there. That either one of those two works. Does that kind of make sense? Yeah. I need to come up with a second option, because some people didn't have a place to put it where it was out of arm's reach, but I could still see the computer. And if that's the case, then that's the backup. You're welcome. Yeah, I know it's such a pain in the butt, and I'm sorry about that. It's just, I really want to make sure that all of you guys who are working really hard, who really know your stuff, that people don't cheat, because that's happened last test, which was distressing. Reminder about the final. You get one-page notes both sides, but you can also do 4 half sheets, or you can do, you can do any combination, as long as it adds up to 1 page of notes both sides. So you can have 4 individual half sheets that are, one-sided half sheets, or you can have 1 page that's both sides. It's a half sheet both sides, and then two other small half sheets. Whatever works for you. So any half pages you want are fine as long as you have a total of 4 half pages one-sided. Also, obviously, you can use your tables, match your formula sheet, calculator. Mac users, make sure you turn off the pop-ups, or else it might kick you out. And PCs, make sure you restart your computer to clear your memory. And you guys all know you have to upload your exam work pages in assignments. And then this is a study guide, which I think most of you guys are aware of also. The problems you need to study. I think there's one problem that I said in there to skip, so don't do that one. Quick summary of Chapter 10. All right, so it's going to look like, it's going to have sort of data that looks like this, or might look like, more likely it might look like, this, right? And that's the one where you have categories here, but no categories here. And that's kind of the easiest way to tell that you've got something going on. And these are kind of in matched pairs. You've got two different variables, age and wealth, which are not the same thing. And they're not observed and expected. Well, it doesn't matter because you don't have categories over here. And then, so what do? Well, this one, the H naught is rho is equal to 0, and rho is not equal to 0. That's the step 1. And then you're going to do step 2 from the PPMC table. And that's where you're going to draw that little line. And you're going to take your PPMC value and shade to the right. And you're going to take a negative of it because this is always two-tailed. So you don't care whether it's negative or positively correlated, just that it is. So then again, remember that this is the shaded area is always going to be your rejection area. It's when you get something unusual. So these spots out here are the unusual areas. Those are the reject H naught areas. To get something in here, then my H naught says that I'm right here. So if H naught says I'm right here and I'm in this area from here to here, then H naught seems correct or could be correct. But if I get way out here, then H naught, I am not here. I've got to be somewhere further out. Right? Because remember, H naught says I'm smack dab in the middle. So anything in here, that's reasonable. You could maybe be there. But out here, you're not going to be out here. If your mean is really here, you're not going to get a sample out here. Okay. So then what you'll do is you'll do a test stat. And your test stat will give you a value, and you'll see where it falls in this line. So this is a summary, right? Your hypothesis, H0 and H1. Find your critical value from the PPMC table using alpha. Degrees of freedom n-2, and then find your test stat. Do not do any formula, just put your x's into list 1, your y's into list 2, and do stat test when reg t-test. That will give you your R, which is your test statistic. Test statistic is R. It will give you your y equals a plus bx. It'll tell you what a and b are. It'll give you a p-value if you want to look at a p-value. So it gives you all sorts of great information like that. And then you need to decide whether or not to reject H0. And again, you really want to go by where you fall. So you can just use that. That's the easiest way to do it is what you are used to doing, which is if I get something over here, I'm going to reject H0. If I get something over here, then I'm not going to reject H0. And that's sort of the simplest way to do step 4. It's what you're used to. Right, so in other words, rejecting H0 means it is a line. Is a line. Don't reject H0, then it is not a line. Not a line. And that's kind of helps you out with the second part. Because rejecting H naught means that you're close to 0 or you're close to 1 or negative 1. Because remember, these guys out here, these guys are negative 1 and positive 1 out here. And then you have your critical values in here. So, if you're out here, that means you're close to 1. It means you're close to a line. 1 is a perfect line. Okay. And then summarize for the claim of the variables. So this is just as simple as doing something along the lines of either enough or not enough evidence to say there is a correlation between blank and blank. That's all you have to do. So that's step 5 for you right there. Okay. Then 11.1 was that chi-squared. Oh, wait. Sorry, we're still in chapter 10. So the second part of chapter 10 is going to be where I'm going to ask you to approximate or predict. So this is prediction. So part 2 is predict. If you rejected H naught, then you would use, then your data is a line. I found this last time, so this should be easier. Yep, there you go. So the line, so you have that linear regression line, right? Y equals A plus BX. And for any X, you can put that in and find predict what the Y should be for there. But you should only use it when there is a correlation. In other words, you should only use it when you reject H naught. Otherwise, if you're not rejecting H naught, then down here at the bottom, do not reject H naught. Then that's when R is not significantly different from 0. Then you would just use Y bar, the average. Y bar. Yeah, if it's not a line, then you just use the average Y. That's correct. This is not ANOVA. This is linear correlation, chapter 10. So how do you do that again? You put data into X and Y. So stat, edit. And then here you have some X's, yes, and Y's. And then you'll go to stat, test, arrow up to get to linear t-test of L1 and L2, frequency 1 not equal to, and then you'll calculate. And they'll give you your A and your B, and I'll give you your R. See, this is a terrible R. I'm probably not going to reject H naught, so I would not use this A and B because it's not a line. So if it's not a line, even though I have an A and a B, that line is kind of meaningless. So it makes more sense to use Y bar. Because if you kind of think about it, so here's my R. So if I look at my, use a different color here. Here's my regression line, and I have it needs to be 0.711. Say, for example, negative 0.711, and I'm at 5 point something, so I'm right in here. 0.5, I don't remember what it was, 0.5 something. So I'm not going to reject H naught. This is this case right down here, where my data is not a line. And it doesn't seem to be a line. It's, you know, my data is, makes sense. My data is 4, 5, 4, 8, 5, 9, and 2, 6. It's not a line. So instead, I'm going to use the average Y to predict. So stat calc 2 bar stats, because I have an X and a Y, of L1 second 1, comma, second 2. So stat 2 bar stats of L1, comma, L2, and that will give me my X bar. I don't want that though, arrow down. There's my Y bar, 7, right there, done. Usually will be a decimal, but in this case, it happens not to be, just randomly. Again, the way to think about that is to kind of remember, you know, can we all agree that height has nothing to do with your test score? So there's no correlation between them. So my best guess at the test score of someone who's 6'2" is whatever the class average is. That's my best guess, right? The Y bar for the class. So again, how do you get the regression line? You use your TI calculator and LinReg t-test to get it. And if it's not a good predictor, then you just use Y bar. So you'll get something that will ask you to predict. So you have to kind of look and say, oh, 40,000 cars, is cars X or Y? Okay, that's my X. So I'll put that in for my X, and I'll figure out what my Y is. The second kind of problem we encountered was firearm deaths. So, not firearm deaths, sorry, this is an example, firearm deaths. So here, what kind of problem is this one? Well, I have categories. You kind of read through it. I have percents, but I don't have just 1%. I have a whole bunch of percents. And they're in categories. 74% for accidental, 16% for homicides, 10% for suicides. So these are categories. And I also have these guys here, observed values. So this is that whole chi-squared list, right? Chi-squared list, where I've got percents, categories, but I only have one list of them. I don't have a matrix of them. I only have, you know, one type of thing. I don't have how people died. I didn't have, you know, gender on top of that. If I did, then it would become a table, but I only have categories in one direction. Over here, these are just the observed and the expected. And really, it's really this right here, these are my observed. This is a whole separate list. So this is one list. This is my expected list. They're two different lists. So let's see, how do we solve that? Well, just as a quick hint to remind you guys that whenever you have that, the observed, I'm always going to give you those. You're going to be given those in the problem. The expected, you always have to calculate. And for the chi-squared list, you got to calculate all of them because there's only going to be 3 or 4. There's not that many, right? The chi-squared matrix, there could be a lot of them, so I'm not going to make you do that. But chi-squared list, you have to calculate all of them. There's only going to be 3 or 4. And it's either going to be where I give you percentages, and you multiply that percent by the total, by n, to figure out how much goes in each group, or I'll say equally preferred, or same proportions, in which case you take the total, whatever the total is, you divide it equally amongst the categories. So you divide by 3 in this case because there's 3 categories. So this is kind of a quick summary of this. All right, your first step is going to be H0 is that your observeds equal your expecteds. H1 is that your observeds do not equal your expecteds. And then step 2, you're going to look up the critical value in the chi-square table using the number of categories minus 1. And then you're going to draw this kind of very steep hill that kind of runs out. And then you're going to shade, again, remember it's only right-tailed because it's positive always. So this is 0 here, and it only goes to the right. So it's only right-tailed. And then you're going to find your chi-squared. You're going to calculate it using every observed minus its expected squared divided by the expecteds. And then you're going to add all those up. And you're going to stick that in. If it's out here, you're going to reject H0. If it's over here, then you will not reject H0. It's the same sort of idea. And the shaded region is the guilty region, the rejection region. The non-shaded region is the non-rejection region. And then you're going to summarize findings for your claim. And all you have to do with this one is just simply say blank evidence, either enough or not enough, that the proportions equal what we expect. That'll work. So that's kind of the basic generic one that should match for anything. If you have enough evidence, the proportions equal what you expect. So the percentages equal what you expect, proportions. So that's just as good. So either you have enough evidence or you do not have enough evidence. So the proportions equal what we expect. That's it. Straightforward, super simple, not hard. H 11.2 is similar. It's also chi-squared, but this is the matrix. So in this one, you have categories across the top and along the side, both. This is the one that has categories here and categories there. So you have this matrix. So this is the chi-squared matrix. It's very similar, and it's also quite straightforward. So again, you have your hypotheses, but you can just do O sub I. Oops, it's not working. O sub I equals E sub I, and O sub I is not equal to sub I. I'm totally fine with that. And then you need to find the critical value. And remember, we use degrees of freedom as number of rows minus 1 times number of columns minus 1. So then once you find it, you're going to do the same thing. You're going to draw your little picture and shade, same as the previous one. And then you need to find the expected values, but not all of them. I'm only going to make you find the first and the last. This is the formula for that. So you're going to find his, which is his row total times his column total divided by the grand total. And you're going to do it also for the last one. Here's the last one. His row total times his column total divided by the grand total. So you just have to find those two. The first one's called E11 because it's the first row. Remember RC, row then column. And then once you find just those two, then to find your stat test, your chi-squared, you can just use stat test chi-square test. You can put this into matrix A, and it will compute matrix B. You don't need to put anything in a matrix B. It's going to overwrite whatever's in matrix B and put and input the expected values into there. And I'll give you a chi-squared and your p-value. So if you go to your calculator and you go to second and then down to matrix, which is this one down here, the fourth one down, it says matrix, kind of is up a little corner there. You go to edit, and say you want a 2 by 4 matrix. And I'll give you a 2 by 4 matrix. You input all your data in, Uh-oh. Oh. And then you'll do your stat test, chi-squared test. This one up here. Some of you may have a GOF test, which is the 11.1 test, and you're totally free to use this one. You still have to show me your work though of what blank minus blank squared divided by blank. But you're totally free to use this to calculate. That's totally fine. But I can't have everybody do that because the 83s don't have it. And then on this chi-squared test, observed is matrix A. The matrix is with these little square brackets around them. B is, again, you don't put anything into B, it puts something into B, and then you calculate. And that gives you your chi-squared and also p-value if you wanted to. So we know this is not unusual because it's 30%, totally not unusual. So we should not reject H0. We go ahead and throw that into our little spot, and you'll see that you don't reject it. It should fall in that white area. And then, step 4. So again, it's pretty typical, right? This guy was in the rejection area, so we're going to reject. If it, like my 3.6 falls over here, so we would not reject him. So either you reject H0 if you're over here, or you do not reject H0 if you're over here. And then step 5 is either you have enough or you do not have enough evidence to reject claim that proportions are equal. That's it. Or you can even say to say that proportions are equal. You don't even say reject claim. You say enough evidence to say that proportions are equal, or not enough evidence to say that proportions are equal. That's totally fine. Don't even have to worry about this part. You can just say, just say it. That's okay. I'm going to be super easy. Or you can do reject claim. That's okay too. I'm fine with either one. And the last thing we talked about was this one here. What kind of problem is this? Anybody? Anyone? One person knows? 2 people? Right, so I have categories here, but I do not have categories here. So this is ANOVA. Because really what this is it's a list. Here's a category and all the data that goes in that category. So in other words, these are groups. They're actually not really even categories, they're groups. There's a small sedan group, there's a luxury group, there's a sedan group. And what we've done is we've sampled 4 people from this group, 5 people from that group, 3 people from that group, and this is their data, their actual data. The other thing, when you know it is, it talks about means. That's a hint that if you have 3 or more means, and they're talking about means, and that's ANOVA. ANOVA is pretty straightforward. You've got, your first claim is, is that the means are the same, and then H1 is at least one differs. You find your alpha, compute your p-value by putting each list into list into a list, and then do stat test ANOVA. Again, this one's a little bit different because we're comparing p-value to alpha to see if it's unusual or not. So remember, our guideline for unusual is 5% or less, typically, alpha or less. If p-value is less than alpha, we'll reject H0. So reject H0 if p-value is less than alpha, if it's unusual. And then the summary would just be either you have enough or you don't have enough evidence to say means are equal. That's it. It's close enough. That is all that I'm going to require for this one. Oops, didn't mean to do that. Okay, and then again, this is a quick summary of what I've talked about this. It feels like a million times already, right? So we had 3 different main areas. We had chapter 10, which is that correlation regression. And you're going to be making a prediction. And then we had, and we have two different datas. So we had two variables and their numerical data. This one down here, these are all categorical. You have categories, your data is categories. And so you have frequencies and proportions involved in there, and observed and expected. So you're either going to have one variable, which would be your chi-squared list, or you have two variables, which is your chi-squared matrix. But here, you know, your answers are categories. And this last one here, again, your answers are numbers, and they're in 3 or more lists for you to run data on those numbers. This is just, I've shown this before. This is something I kind of put together, which is another way of kind of maybe trying to sort it out is to figure out how many variables you have. And that doesn't mean how many categories you have. Category is not a variable. The variable is what you actually ask the person. You know, what is your height? That's a variable. Or what's your favorite color? That'd be a variable. The categories, if your answers to that are categories, that's a chi-squared. If your answer to the question is a number, what's your height, then that would be, you know, this linear regression area or the ANOVA, depending on whether it's one question I'm asking them or two different variables I'm asking. If I ask you your height and your test score, then we're looking at linear regression. If I ask you just your height and, you know, and then I try to figure out what group you're in, and okay, what's your height? Okay, so you're a student, or you're a teacher, or you're neither, and I'm comparing those heights, then that would be ANOVA. But if your data is categories, then, you know, if it's two variables, then that's a chi-squared matrix. If it's just one variable category, then it's a list. All right, and then we also kind of took a quick look at this one. Frequency table and make a histogram. No, you do not need to make a histogram this exam. I shouldn't necessarily tell you that, but you don't. Definitely not a polygon or ogive, and not a histogram either. I'm not making you guys do that, any of those things. Okay, so this one, if you kind of look at the data, you can see right away these two only have things along the top. There's nothing along the sides. So these ones are not chi-squareds. So instead you have lists of data. So this one is 3 or more lists. That's ANOVA. This one is only 2 lists, and they're matched up, and they're different things. One's an X and one's a Y. This is chapter 10. These other ones down here, they have categories across the side and the top. This one is your matrix, chi-squared matrix. I have to take off the X's because those are confusing, I think. And then this one here, there's really only a list. It's really just a list that's, because this is an observed and an expected. So this isn't really, these aren't really true categories. It's just observed and expected. So that's why it's this chi-squared list. I would like to spend just 5 minutes going through some of these with you guys to help you figure out what kind of problems you have. You do need to know how to do them, oh, we kind of did one similar to that. That's okay. Oh, I want to do this one. Shoot. All right, I'll do this one with you guys. And I really want you guys to, later on, go through what kind of problem this is, because it's really important you figure out kind of how things go. But this one's important. Who's here who's not from the night class? The night class did this. Is anyone from here not from the night class? Evan and Megan and Aria, right? And Rosie, you're not from that class either, so you guys didn't do this. Oh, and Yuan, you didn't do this either. So this one, shoot. I feel like you guys should do this. You will have to make a frequency table, but not a histogram, polygon, or ogive. Oh, this is a different comment. So once you guys take a minute, 2 minutes, and try to figure out how to do this problem, and I'll give you another hint. It will also have this on there. I'll also say assume it's normally distributed. So that will be a hint that you'll have. Assume normally distributed. I'm going to go back into my exam, make sure I did that. Take a picture of this. Never enough time in a review session to do everything I want to do. Okay, do you guys remember this one? So, weights of rats have a mean of 115, standard deviation of 16. What's probably a rat weighs less than 112 grams? Yes, I'm not going to make you guys do histogram, polygon, or ogive. Okay, so this is going to be a normal distribution. So that's, if I look kind of back through my notes, I say, oh yeah, that's where step 1, I find the z-scores. Step 2, I draw a picture. And then step 3, I use normal CDF to find the area, which is the same thing as probability. All right, so find my z-score. Okay, so that's going to be, my z-score is going to be my, this guy is my, what I'm trying to find. Whoops, let me go ahead and do that in a different color. All right, what is the probability that he weighs less than 112? So that's my item of interest, that's my x. So I'm going to do x minus mu over my standard deviation. So that's going to be 112 minus 115 over 16. And you guys got 0.1 88, I think is what people got, something like that. So then you'll draw a picture. And you put in 0.18 negative, oh, so it's negative. Negative 0.188. And you want less than, so you're going to shade to the left. And then you'll do normal CDF. Of negative 999, comma, negative 0.1, I think it was 88, something like that. And has anybody got an answer for this yet? Oh, 875, sorry. Okay, yeah. And you got, what did you get for your area? 0.4256. Perfect. Great. Thank you. Thanks, Vicki and Haley. And then it goes on to say, if you randomly select 36 rats, what's the probability their mean weight is less than 112? How is this different? How is this problem different? Well, it's because we're looking at 36 rats. So now we have an N. And whenever you have an N, then you have to use sigma x bar. So then you have to say, oh, wait, I'm going to use a new sigma, right? That new sigma which is the old sigma, divided by square root of n. So it's going to be 16 over square root of 36. So that's going to be 2.67. So now when I do my z-score, it's going to be 112 minus 115 over 2.67 instead. Oh dear, that's all messed up. Just saved up. It all came at once. Okay. So then you end up getting negative 1 point something. 1 point, I don't know, we'll call it 1.1. And then we'll end up doing, let me know if someone gets an answer. 125? Normal, thank you. Normal CD. Oh. All right, well, either way, so we're going to go from negative 999 to negative 1.12, I don't know, 5 or 4, doesn't matter, either one. And you will get almost the same answer either way, which will be anyone? 0.14 something? Now let's try it. Okay, so go to a calculator. And so here's a couple of hints. On your calculator, there's really only two things you're going to use. It's either going to be stat, and you'll have stat edit, which is your list, stat calc to do, you know, some of your one-bar stat stuff, or stat test to do all those other cool things. The other thing you're going to do, so that's a stat key, the other thing you'll do is just second vars. So if you can't remember which one, just try both of them and see which one seems like, oh, yeah, that's what I want, you know. So normal CDF is right there. And they're going to put in negative. Remember, negative has to be this one right here, not the minus sign, you're going to get an error. And likewise, if you go to subtract, you can't use the negative sign. You have to use the subtraction sign. Comma, negative 1.12. We'll do 5 because I think that's what the class had. As 0.130. So 130. Good enough. All right. So nobody left now. Is everybody gone? So let's just do like a few of these just so we can kind of help you guys sort this out. So what kind of problem is this one? Okay, well, we've got percentages here, and we got 34 out of 710, so it's some sort of proportion thing. So is it a chi-squared? Because chi-squareds are proportions. But things, I only have one percentage. I don't have a whole bunch of them. I don't have, like, different groups, like 34, like 8 a.m., and 36, like noon, and 27, like, I only have one thing, and it's yes or no. So this is a regular ordinary proportion from chapter 8, 8, 9, 10, 7, 8, 9, sorry. And is this so proportion, am I going to use a Z or a T table? Yep. Z table, remember, easy peasy. And then is this going to be, so you guys remember those things, right? Easy peasy. Easy peasy, proportion, use a Z table. And this is a test, hypothesis test, because I'm testing my claim. Good. Next one. What kind of problem is this? Take 15 seconds and I'll ask you guys. What do you guys think? What kind of problem is it? I have categories, labels, but I don't have anything along the side. So it can't be it can't be a matrix because I don't have anything on the side. Oh, and then there's a mean. So this has got to be, so because I've got, 3 categories with things down below it, then this has to be ANOVA. This one? I see the word mean. It helps me out a little bit. But it can't be ANOVA because I don't have a bunch of lists. I need to have 3 different lists. So here I've got a mean, and I've got 1 sample, 2 samples. So this is a regular ordinary mean. So am I going to use Z or T for the Z table or T table? T table. Yep, mean Mr. T. Mean Mr. T. So I know that means use T tables. And is it, and it's 2 samples. And then is it a test or a confidence interval? Yep, test the claim, hypothesis test. You guys are all going to do well. This one? Confidence interval, exactly. Confidence interval. And is it a mean or a proportion? Yep, mean. So it's going to be a T table. Do you guys remember how to do this? Should we go through one quickly? It's been a little while since we've done one of these. So this one, your best point estimate is going to be your sample mean, X bar. This is my X bar. This is my S. So best point estimate is 33.6 because that's what I got from my X bar. And then I need to find my margin of error, E. So that's going to be, well, let's see, it's my critical value times my S over square root of N. S over square root of N. Let's see if I can make that happen. So critical value, need to look that up from the table, which I don't have a table handy. 15 race car drivers. I bet I do have a table handy. Let's see. T table. And this is going to be a mean Mr. T, so it's T, and 90% confidence interval. So 90% confidence interval. Degrees of freedom, 14. 90% confidence interval, degrees of freedom, 14. So it's going to be 1761. Okay, good. So it's going to be 1.761 times my S, which is 7.67 over square root of N, which is 15. And then, whatever I get for that, I don't know if I want to, no, I guess it won't take too long to find it. All right, so let's go ahead. We'll bust out the calculator. 761. Oh, turn it on. Let me find square root of 15 first. Okay, so I'm going to do this, raised to the negative 1 power, times 7.67 times 1.761, and we'll get 3.487. So the last part is my confidence interval. Which is going to be, it's bigger, it's going to be parentheses x bar minus my margin of error, comma, x bar plus my margin of error. So we end up getting 33.6 minus our parentheses. Is that 3.45? 3.5, comma, 33.6 plus 3.5, which gives me 30.1, comma, 37.1. And there we go. So I know it's been a while since we've done those, so I thought it might be worthwhile just to kind of take a look at one real quick. So don't forget, margin of error is E. They're the same thing. So I guess my next question to you guys is, it's getting on to 2 hours. We should just do a couple more of these. So what kind of problem is this? Right, I have categories, and I have them observed, but I only have one list of them. I don't have a whole matrix of them, so this is a chi-squared list. Whoops. What's that one? So some people kind of thought this was a list as well, but things, I don't have any categories. It can't be a chi-squared list because there are not categories here. So it can't be that. And then also there's the word, there isn't. But I have a mean. Do you guys see that one? So this is where I have data, and I need to find this. I need to find my own x bar. So this one is a hypothesis test, mean. So we're going to use the t-table. And I'm kind of rushing you guys a little bit on these. I really think you guys should go over them again. We'll just do 2 more. How's it sound? So which one is this one? So I have labels here. I don't have anything here, so it can't be a matrix. And I don't have labels there, so it can't be a chi-squared, any kind of chi-squared. And I only have 2 lists, and they're different things. So this is my chapter 10 linear regression. And then also there's this prediction thing you have to do later. Okay, and then I think this one is good. Oh, this one's too quick. That's too easy. You guys would nail that one so easily. This one. last one. So yeah, so this, we have percentages, right? So this is definitely in that proportion sort of thing, but I have more than one proportion. I have a whole bunch of proportions, so it can't be a regular chapter 7, 8, 9 proportion because I have too many proportions. So instead, I look for categories. We've got plastic, we've got paper, we've got reusable. So this is 3 different categories. So this is going to be a chi-squared list. So it's kind of hidden in there. It's not, you know, I didn't have 2 different things. I have a matrix, right? It's not that. So it's got to be, in the matrix I have to give you the data like that. Okay, good. And then just for, you guys already got that one. And you guys probably already, you can tell already that this is a chi-squared matrix, I hope. I hope that's kind of obvious because I have categories along the top and categories along the side, so I got my matrix in here. Okay, good. All right, well, great job, everybody. Thanks for staying with this. And I think actually most of you guys did actually stay, which is impressive. So well done. And good luck on the final. Are there any questions before we close this up? Yes. The GeoF. You still have to, so let's go to one of those. So this one is one of them. You still have to give me this. Chi-squared equals whatever this was, 28 paper minus whatever I expect to get, 8 minus 24 squared divided by 24 plus whatever the next one is, 120 minus plastic, 32, 96 squared divided by 96. You still have to write that out for me, but then you totally could go to your GeoF test, and I'll show you how to do that if you want right now. So the way you do that is you go to Stat, Edit, you put your observed, let me clear this, clear Enter, over to here, up to that, clear Enter, and I'm going to put in my observed into list 1, so that's 28, 120, oops, okay, oh, oops, no, second, quit, okay, so 28, stat, edit, 28, and then 120, and then the other one was the rest, so that would be 152, and then over here we have our expected, which is 24, 96, and 180. So then you have observed in list A, list 1, your expected in list 2, and then you do stat, test, GeoF test. And my observed are in list 1, my expected are in list 2, my degrees of freedom is 2. So make sure you get that right, and then calculate it. And that will give you your chi-squared and your p-value. I wonder if I screw that up. So say I did stat test, GeoF test, and I put the wrong degrees of freedom in. I left it at 5 because I didn't know better. It's still going to be the right chi-squared, but my p-value will be screwed up. It'll just mess up my p-value, that's all. So it's not a big deal. So it still gives you the chi-squared, which is what you want, what I think you guys are all looking for. So that totally works. And you can just write that in. And I don't know how you found it. I assume that you did the work. But you can do it that way too. I don't care. I don't care how you find it. Just as long as you show me the work up here. Good? Any other questions? Well, you should write down, I guess, the charts, like how to tell maybe a chapter 10 from a chapter 11.1, from a chapter 11.2, from a chapter 11.3, from a chapter 8.9. Oh, you don't need, yeah. So I'm not, you won't need, I'm not gonna make you do a chart. In the past, I've made people do a very simple histogram, but I kind of got away from that just because, you know, they're pretty straightforward to make, and there's programs that make them nowadays, so I kind of have not really pushed that the last semester, 2 semesters. So you don't have to worry about making any graphs. Yep. Yeah. Any other questions? Can I use this for both chi-list? Okay, so that's for chi-list, the goodness of fit. For the matrix, it's different. The matrix is this one: stat, test, chi-squared test. That's the matrix. So that's the one where you put in, you input your data into A. So that's the 11.2 chi-squared matrix one. The goodness of fit is for the lists, and lists only. Okay. I guess that's the last question. I'm going to go and stop the video.